So, what I was saying is that we talked about Indian design sky, and if you recollect that it was B theta is equals to B z cosec theta, theta greater than 0, no not 0, pi by 12 to pi by 12 to theta greater than pi by 12 to pi by 2 greater than equals to pi by 2 and equals to B z cosec pi by 2 pi by 12 for theta greater than 0 to pi by 12. So, this was they assumed a sky which is very its brightness is very high near the horizon. Some measurements must have been done, but then this was Indian design sky, and that is what you find in the code, and that is what we talked about earlier. But there, as I said, there are a lot of changes actually, and possibly Indian code would also need a change, because there has been a lot of experiments, global experiments, but largely they were in the not on tropical climate, but even some measurements were done in India as a part of a global program. So, from those kind of global program, the first one that we look into different types of skies. One of the non-uniform sky which was proposed somewhere around 1996 looked like this. B, so they started even there, if you see in earlier we talked in terms of B theta was equals to B z cosec theta, right, B z cosec theta. So, you actually relate this brightness of the sky. In this earlier case only we are doing it at a design point. So, therefore, it corresponded to a specific time and specific part of the sky's horizon. If you remember, we were talking about this horizon or the quadrant which is opposite to the sun, opposite to the sun. So, at a specific time, which means we are fixing up according to a particular this theta is essentially the altitude of the point or altitude of the point in the sky where I am interested in brightness. Now, that is defined here in terms of beta Bs. I am calling it beta Bs because code uses theta. So, we are using that notation theta. Beta S stands for the elevation angle, if I may call so, elevation angle of a particular point in the sky horizon, right, that is why S. So, I choose any point in the sky, a small element, and this angle is B beta S and divided by B z. So, here also you see it was all ratio B theta by B z, S cosec theta, very simple function it was used. For a non-uniform sky, sometimes people propose something of this kind, that for the illumination at any point in a sky element. So, let me draw it like this, let me draw it like this, let me draw it like this. So, that is my sky, right, that is my sky, and consider some element somewhere, right, and somewhere, and this is its angle with this angle I am calling as beta S. Beta S stands for sky element. I am using notation consistent with whatever we have used earlier. Since beta is the notation we use for altitude angle, to separate it from altitude angle of the sun, I have put in a beta S. S stands for sky element, right, or beta sky one could have called. So, ratio of this is given, and this is written as 1 plus sine. Earlier it was cosec, 1 plus sine plus. Now, this would correspond to a zenith angle, because zenith angle of this element in the sky, zenith angle of the sky element. So, if I know the zenith from there, this is a zenith angle. So, that is we are calling as ZS. So, sin beta s is nothing but cos beta cos ZS. ZS is the zenith angle, the angle this point makes with the 90 degree minus beta s, 90 degree minus beta s, 90 degree minus beta s. So, this was one of the skies proposed earlier, right. So, B is the brightness subscript beta S, and Z stands for sky element and their zenith respectively, right. So, this is the sun's, Z will be sun's zenith, Z will stands for sun zenith, and for sky element the subscript, this subscript S, not this. B is the brightness subscript S stands for Z, beta stands for altitude elevation angle, Z stands for sky element angle, zenith of the sky element angle, and S and these are the angles, basically Z stands for the zenith angle. So, we will make a diagram and show it. So, then International Standard Organization defines sky in terms of these ratios, right, these ratios. So, this diagram that I was talking about looks something like this. You see, this is your horizontal plane, this is the sky element and this is the sun, right, this is sky element, this is the sun. So, this is my, and this is the zenith point, this is zenith point, zenith. So, this is the zenith point, it is kind of a trying to show in 3D. So, this angle I call as Z, this angle will be sky element makes a ZS, this I am calling as. So, this is this I will come to this later on, this is ZS and this is your beta S, that is how I am defining beta S sky element, and this is our normal Z is here, zenith angle of the sun, that is what we have used so far. So, I did not want to put a subscript here, and this is what is this is beta, altitude angle of the sun, that is what we have used so far, altitude angle of the sun is beta, and the angle between these two, I am calling is I will just define 1 minute, because okay, now sun's position I define by two angles, one is that altitude angle beta, other is the azimuth angle from north. So, if this is north in the horizon, so this is azimuth angle of the sun, azimuth angle of the sun is like this. Similarly, azimuth angle of the point that of my interest or sky element is theta sky. So, it has been made now more general, you can find out the brightness at any point in the sky as a sky in terms of the zenith brightness, that is how the functions are expressed. So, these two elements, so this is ZS and this angle we are calling it this, what is this notation? Chi, actually I think it is chi or something, whatever it is. So, this is what is used, standard use. So, this is the angle. Now, you can see there is a spherical triangle. What is a spherical triangle? This is the spherical triangle, right, and this is one arc, this is another arc, the side arc actually, and this is a third arc, and this is the angle between these two arcs. So, I can actually find out the difference in the azimuth angles, because that is something like wall solar azimuth, the difference between these two is something similar to wall solar azimuth we talked about. So, this angle, which is the included angle between these two arcs or two sides, that can be related in terms of this arc angle, this angle and this angle, right. So, this is what is done. Anyway, I will come to that angle later on, but just before that, so one of those ISO sky suggested was something like this, B beta S divided by B Z is 1 minus exponential sin beta S plus point some constant 10 to the power minus 3 into to the power k and cos square. So, you can see that there is a function involving this ratio is a function involving this, how much it is away from the sun, right. So, that's more it is away, this angle is nothing but the arc distance, more it is away. So, it is 10 to the power minus 3 chi, this one, which means that more this will be, this value will be smaller, and cos of this angle again cos angle is anyway fraction. So, square it up and so on. So, this will be related to this, this angle, brightness would change depending upon the distance from the sun, right. So, if it is opposite quadrant, actually you can find out that would be essentially exactly opposite, means 180 degree it would make, right, 180 degree should make completely opposite, 180 degree should make, because this 2 pi. So, pi angle it will make exactly opposite quadrant, exactly at the opposite point, and then this is function of this angle. Then there is a function of this z angle, zenith angle, function of zenith angle, and there is a constant. So, also this function of this beta s is nothing but cos z s. So, it is a function of zenith angle of the point, zenith angle of the sun, sorry, this is z s, yeah, function of z s, sin beta s is nothing but cos z s, sin beta s is nothing but cos z s. So, it is a function of this angle, function of this as well, and also function of this angle. So, this angle first let us look at from the spherical triangle. This can be obtained from spherical triangle as cos of this, remembering the same formula that we have used earlier, sin of z, sin of z s, that is what will come, sin of z and sin of z s, and included angle is cos of difference between these two angle, right, because included angle is nothing but this angle, this angle, included angle is this angle. So, this angle is phi sun minus phi sky, where phi is a azimuth angle, this is the same convention we used earlier, and phi of the sky element. So, this I am calling it as gamma sky, gamma sky. So, this angle I am calling it as gamma sky. So, included angle is gamma sky, right, and if I write this formula, included angle is gamma sky, that was cos, and remember this was sin z, sin z s, because this was sin z and sin z s, because we took cross product sin z and sin z s into cos of this included angle must be equals to cos of those two angles, must be equals to cos of this minus, remember this minus cos of this, cos of the third angle minus cos of those other two angles. So, if I take it on the other side, this is what I get the formula, this is solar azimuth with respect to the point, which is phi sun. So, this angle I can find out any point, it is related to the zenith angle of the sun and distance of the, it is related to distance of azimuth angle or wall solar azimuth type, point solar azimuth if I can call it, or solar azimuth with respect to the point. So, it is related to all this. So, that is how I can find out this one, and my brightness is a function of this, my brightness is a function of this, right. So, CIE standard sky proposed this ratio, that is brightness at any point in the sky is given a function of this, like in a similar manner, function of z s, function of z, and this is function of 0. If you put z s equals to 0, that means this is at zenith, this is at z s equals to 0 means this is at zenith. So, if you know the phi value at 0, this function value at 0 and phi z is given. So, this remember this was the form of the curve, I will come back to this, this is the form of the curve. So, this involved z and it involved a constant, right, z is the zenith angle of the sun, it involved a constant and this involved this function. So, exactly, and this is nothing but cos z s. So, if you see that this is how the sky looked like, so its function is something of this kind. So, this is one was that exponential function of z s, sin cos z s was there and exponential function related to this was related to zenith angle, and this is a constant 0.234 or something. So, typically this is how sky is generally now expressed. Now, sky is expressed in this manner. Now, how do I find out f of function, these functions? Let us see. So, B is brightness, etc., that we have already said. So, this function is given as 1 plus a to the power b by cos z s. You can see that it is similar, almost similar to what was there in that equation. It was almost similar to what was there in this equation. It is almost similar to whatever was there in this equation, is cos z s. So, it is a function of z s, it is a function of z s, 1 plus a e to the power b divided by cos z s. So, two constants we have, a is a constant, b is also a constant, and this is valid 0 to pi by 2, because z s will vary, the locations zenith angle will vary, from the sky element to the zenith, that angle will vary from pi to 0 to pi by 2, 0 to pi. So, corresponding to 0 it is at the zenith itself, corresponding to pi by 2 it is at horizon. I am talking of this angle, this is my sky element, this is the zenith. So, this is z s I am calling it, and this angle is I am calling it as beta, yeah, beta s, I am calling it beta s, right, I am calling it beta s. So, this is zs. So, when zs equals to 0, that is at zenith, and this is 1 plus, at 1 plus this equals to cos 0 is equals to 1. So, a to the b. But what about horizon? Pi by 2, this is taken as 1. For pi by 2 it is taken as 1. Basically this value, this is a positive value. So, it actually goes to infinity. Zs equals to pi by 2 cos 0 goes to infinity. So, it is taken as 1 because it is not defined. So, it is a kind of a point singularity or something like that.
If we go a little left to pi by 2, then still that is not.
Yeah. So, it actually it is taken as, this value is taken as approaching 1, right, approaching 1 as phi tends to phi by 2, right. So, that otherwise this value will be very large, this value will be small, it will be very large. So, that is the point, but it is taken close to 1. Okay. So, constants are defined in that manner, constants are defined in that manner, constants are defined in this manner. Supposing b is negative, then all this problem is get solved. So, constants are defined in that manner, right, these are empirical constants. Now, this function is defined in this manner, this function is defined in this manner, 1 plus c e to the power d into this and e to the power d pi by 2 minus. So, there is a similarity, there is a similarity here also, this e is constant, this e is not exponential, this is constant, this e is constant not exponential, e cos square this. So, for f z it is the same function because it is a f function, there are two functions f and other one is, there are two functions I am using, one is this, another is f. F is 1 plus c e to the power dz e to the power d minus pi by 2, e is a constant cos square corresponding angle. So, this is for sun solar zenith angle, this is for the element, the angle it makes the element, and a b c d are c d e are constant depending upon the sky type. A B C D E are constant depending upon the sky type. A B C D E are constant depending upon sky type. So, therefore, these values have been actually proposed. These values have been actually proposed, right? These values have been proposed, and these are empirical constant. So, this has to be determined from experimental work. So, what they did was they had measurements done in various places. Particularly in North America, US and also somewhat in Japan, data were available, sky brightness data are available, they measured them, and one or two might be also mostly in Berkeley and places like that, some in Canada, and one or two might be in places like Phoenix, some of those one or two, but largely it is in non-tropical. But however, there was a global program from where they finally also came out with the constants are not available for Indian scenario, some or other. We have not been able to trace that data in published literature or also on the source. So, whatever it is, so this is how the skies are defined. Now, how this A B C D E varies? You see, there are 15 skies defined. 15 skies have been defined, right? 15 skies have been defined. For example, type 1, type 2, type 15, etc., etc. Now, this is standard sky, this is standard sky, right. There are alternative forms. So, the form this is, for example, this is CIE standard sky, alternative form, steep luminance gradation towards zenith and azimuthal uniformity. So, if there is it does not vary with the azimuth, right. So, this is how it has been described, and A is 4, B is minus 0.7. So, that makes sense, B will be always negative, otherwise if B is not negative, then it will not go to 1, right. So, it is 1 at the that is how the B has been fixed. For C is what is C? For the standard overcast sky, which is overcast sky is by and large luminance gradation towards zenith, and it is uniform all over the azimuth. That means, you take in one quadrant and the other quadrant, it will be same for the overcast sky, right. and earlier this was taken to be completely uniform, but now it is not taken to be is uniform, it is taken like this. So, let us see is the values of E is equals to 0, values of E is equals to 0. So, this term is not there, this term is not there, and this is negative 0.7 or something. C is also equals to 0, C is also equals to 0, D is minus 1 0, D is minus 1, right. So, this would right. So, this as you increase, as the distance increases from the sun, as the distance increases from the sun, right. So, this angle increases, which means that this will be lesser and lesser, but if C is 0 anyway, this term is equals to 0, C is 0, this term is equals to 0. If we go back to this formula, C is equals to, so this is simply coming as a constant. This is simply because C is 0, D has got a value, D has got a value. So, but this whole term will go to 0, E is 0. So, I have got actually this function equals to 1, this is also 1, and but this will be there because B is negative, A has a value 4 or something like that. So, if you see this, A has a value of 4, B is negative. So, D is 1, but D is not relevant if C is equals to 0, because in the formula D comes here, if C is 0, effect of D is not there simply. So, all that is there is A and B. So, if you go back to the formula something like this, this value is we said that it will be 1, this will also be 1 in a way, and this values phi ZS, how is phi related? One of them is 1 plus what is phi ZS is 1 plus a to the power b. So, only this term is there, only this term is there, only this term is there depending upon. So, this is because it is not varying with the azimuth. So, this term is 0, this term is 0, this value is some value is there, a is equals to 4 and b is equals to minus 0.7. So, this value will be a plus b to the power, I mean e to the power minus b over, though some terminology, b was some cos, was it how much cos ZS. So, cos ZS. So, b is actually negative, b is negative, e to the power 1 plus e to a e to the power, that is what it is, 1 plus a e to the power. So, this is negative, this term is the position of the sky element from the zenith, position of the sky element from the zenith. That means, along this height the brightness is varying, but it does not vary otherwise, right. And when ZS is small near the horizon, when it is equals to pi by 2, this value becomes 1, at pi by 2 this value is 1, at all other values when this is equals to 1, this is negative. So, this will become least. So, maximum at the zenith and gradually decreases, gradually decreases, gradually decreases. In fact, stiff gradation, that is what we are saying, stiff gradation, luminance gradation towards zenith, azimuthal uniformity, because it is not varying with the azimuth, therefore, those two terms are equals to 0. Similarly, this is overcast sky with stiff luminance gradation, slight brightness towards the sun, and overcast moderately graded with azimuthal uniformity, overcast, and then sky with uniform luminance 0, a is equals to 0, b is minus 1, right. So, it's uniform luminance, everything is C is 0. So, almost every term goes to 0, d is equals to minus 1 and so on. So, sky of uniform luminance, everything, all those, it will be simply phi z, bz will be same as b beta s will be equals to bz, same, all throughout it is same, all throughout it is same, because these terms are 0. So, that is how these coefficients have been determined, as I said. So, CIE standard clear sky, polluted atmosphere, these values are there, and it depends upon the, because it depends upon the overcast sky. If you see, either there is a total cloud cover, or you have something like highly polluted environment. What you are seeing right now, similar sort of situation, it is highly lot of particles in the system, which is diffusing this, or it is fully cloud cover. But cloud cover cloudy sky, somewhere it is given, I think overcast sky, yes. So, brightness is different, then a somewhat polluted atmosphere, things are totally different. So, this is how this various skies are defined. Now, you have to have, for a given location, you have to have a set of data in order to find out your ABCDE. If you are doing it for 8760 hours, that means 24 into 24 or at least 12 into 365. If you want to calculate out how much daylight will be available, design is one thing. Design is done to find out the fenestration area, but you want to compute the energy that is coming in, so that how much artificial illumination you are saving, then you got to find out for all these days. And therefore, the position of the sun becomes important, right. Position of the sun becomes important because this will keep on changing from day to day and time of the day as well. So, this is position of the sun becomes important, and therefore, if you are to be used in a software must use appropriate sky, because it will calculate, most of them also calculate the energy saving due to the daylight. So, that has to take right kind of sky into account. Now, to find out this ABCD, either you make some notional assumptions or measurements should be available to find out what your ABCDE are. But there is another way of doing it also, that has been also proposed, that is been proposed based on okay, let's first, I mean I will come to what based on. Now, diffused radiation in a completely overcast sky, since we have got two radiation, diffused radiation as direct radiation. Remember that global radiation was diffused and diffused and direct. Global radiation was diffused and direct. In an overcast sky, which will be more? Right. So, what it is done is you can relate diffused ratio of diffused sky radiation, diffused radiation divided by total, that is global radiation, total radiation, that is diffused plus direct. If this is high, what does it mean? It is more towards overcast, right. It is more toward overcast or cloud covered, or is something like more towards possibly one of those skies that we are defining. It can be defined with respect to this ratio, and this data is easily available. This data is easily available. This radiation data are easily available, while brightness data are not so easily available. Sky brightness data are not so easily available, right. So, diffused radiation divided by total diffuse plus direct radiation, diffuse plus direct radiation. If you take this ratio, so I might be able to relate, or something called sky clearness. Clearness of the sky will depend upon this ratio. Clearness of the sky will depend upon this ratio. So, I can define clear sky. A clear sky will have high amount of direct radiation, and diffuse radiation will be less. On the contrary, if it is overcast or like all sorts of covered situation, then diffuse radiation will be more, not so clear sky. So, if I am looking at all these skies can be defined, these skies, standard overcast sky, these skies can be defined, or ABCDE can be related to this sort of a ratio, right. Overcast with luminance, etc., sky, okay, partly cloudy, and the cloudless turbid sky, white, blue, turbid sky with blue, so this is more towards clear sky, CIE standards clear sky, or something for polluted atmosphere. So, clearness of the sky is a function of, clearness of the sky clearness of the sky is a function of, it's depend on the ratio of diffuse to total. So, zenith brightness I can relate to this zenith brightness. So, zenith brightness, what I am calling it B z, I am calling it Bz is my zenith brightness. See, one of the unknowns there is Bz and ABCDE. One of the unknown there is Bz. So, Bz and ABCDE I should be able to relate to this term clearness of the sky, and that has been done, that also has been done, and again it is validated for only certain locations in the globe, not throughout. Some, as I said, some data were available particularly in tropical countries is not much available, but some data is available. So, but one can relate to this, one can relate, but validation of this one as I said ABCD etc. has been done only with respect to certain specific locations, but still this might be more useful one. So, we will look into this in the next class, and also I did not define glareness index. Did I define glareness index? G I have defined, right? What was that? Glare constant. So, 10 log of sigma G I are defined as glare index, glare index, yes. So, glare index I did not define, Gi I did not define. So, I will define that as well, and look into a couple of small computations. Glare constant we defined, just we are defining the glare index, and I think I have told you the size and position factor and all that in the last class sometime, right, and glare index is defined like this 10 log. So, if you can calculate out the glare constant for any source according to the formula, then glare constant, glare index you can find, and this value should be below a specified value, order of 19, 20 etc., etc. So, if we go back a little bit and look at this, the glare, that is what I said 10 log G. So, let us go back a little bit and look at this situation. It was given by 0.24 B0 1.6 omega to the power 0.8 by Bs 1 by P to the power 1.6. So, this using this formula you can calculate out the glare constant for each individual source. For example, you consider a source like, supposing I have a spherical source, right. Supposing I have a spherical source globe, right. If a globe, let us say 5 centimeter radius or something like that, some such, such a globe, and the observer is somewhere there. So, if I draw a normal one, size of the object will be given by pi r square. Size of the object will be given by pi r square, right, and brightness also. If you know the total lumen output, that is flux. So, flux into basically flux divided by 4 pi r square will give you the illumination on the surface, lux, and 1 lux corresponds to 1 apostille. So, if you are using this in apostille, remember 1 lux brightness corresponds to 1 lux illumination corresponds to 1 apostille, otherwise 1 by pi candela per meter square. So, you have to have a pi relation. So, now if it is an apostille, you can calculate out accordingly. So, similarly surrounding brightness or surrounding lux is known, and reflectivity of the surrounding is known, because there will be, you know, so reflectivity multiplied by the lux level, that will give you the brightness in apostille again. So, this can be calculated in this manner, source and the surrounding, you know, object and the surrounding you can calculate, and position factor has to be taken from a table, as I mentioned. So, that is how one can calculate out the glare index. So, for example, if it is a flat lamp, rectangular lamp, no louver, the size will be full size, right, size will be full, and brightness you can of course find out from the lumen output of the lamps that are inside, and if there are some louvers like this, then the effective size will become this much each one. So, each one separately has to be considered and summed up, right. So, that is how it is done, but then angle would change for each one of them, because if somebody is viewing from here, let us say, so these angles are different. So, position factor will actually change a little bit. So, that is how we calculate glare, right. So, continuing with the sky, see this idea of Perez model actually boils down from this. If you see the solar spectrum, right, radiation as a function of the function of wavelength, right. So, only about a small portion in the center, as you can see, this is what we see, right. So, this is what we see actually, this is a nanometer. So, solar spectrum, this is in, you know, this not nanometer, 0.5, this must be in, you know, like this is 550 nanometer. So, 0.5 would be, what would be the scale, multiplied by the corresponding scale, multiplied by this corresponding scale. So, therefore, it has something to do with the radiation that is received itself. This is the portion, this is the portion, this is the visible portion, this is the direct spectral irradiance, this is the wavelength. So, this is the total solar radiation. Of course, you know, a large amount of infrared radiation heat waves are there, and this is the visible portion. So, therefore, it depends upon this total irradiance that is received. So, one can relate the amount of light to the total irradiance as well. That is the idea. That is basically the idea. You know, that is basically the idea. So, that is where Perez model stands, and he defines three terms: sky clearness epsilon, which is given as I diffused radiation. That is what we have used the notation earlier. I beam radiation divided by I diffused radiation, right. So, then some constant, of course, this is zenith angle depending upon position of the sun, right, this is depending upon position of the sun. So, k is a constant, this is been proposed as 1.041, zenith angle of the sun, where the sun is, if it is in the horizon. So, it is related to that. So, that is the kind of sky clearness is given, which is the ratio of total radiation, global radiation divided by diffused radiation, you know, relationship between these two. Because as I said, if you have higher total radiation, you are likely to have, I mean, you know, basically the visible portion is also proportional to that. So, one can relate to the radiation, but clearness is related to more the direct radiation. It means what? You have more clear sky, more the direct radiation, you have more clear sky. So, more IB beam radiation diffused compared to diffused radiation. So, this number will increase with sky clearness, this value epsilon will increase, because this ratio is, if you know, it is 1 plus IB by ID, this part. So, if my ID is large compared to IB, it means it is less clear. Overcast sky means I have got large ID, very little direct beam radiation, you just do not see the sun. Overcast sky, you will not see the sun, but still you will see the, you know, the daylight is still available. So, clearness, sky clearness is defined by this, right. Then he defines one more thing called sky brightness, which is m divided by ID by solar constant. This is actually solar constant that we talked about. How much of it is reached at the diffused radiation, how much of it reached at the ground compared to the solar constant. Now, it would depend upon turbidity of the atmosphere. So, m is called optical mass. If you have, it would depend upon cloud condition as well as level of pollution. Industrial area, this would be different than less industrial area, etc., etc. The particulate matter in this, atmosphere and so on. And this is anyway solar constant. So, in the model proposed by Perez, where he tries to, because radiation, the data for brightness of the sky may not be available everywhere, but this was validated for, as I said, only for mostly for subtropical climates, not for tropical climates. And A, B, C, D, E, if you remember the E also, A, B, C, D, E of the model that we talked about earlier, clear sky model, they depend on epsilon and m and also on the zenith angle. They depend on epsilon and m and zenith angle, and they have actually given some empirical curves or formula related to this. So, that is what that model is, Perez model is. So, I think that is it. So, these are related to sky. Now, once you know the form of the sky, we have already integrated it and seen that how you can get it, how we can compute the illumination sky component at any point, that we have seen. But all this 1 point passing through the corner is required only for using the table. Supposing you are writing a program of your own, today it is not necessary, because you can do numerical integration. For example, the window you can divide into very small areas. It is not really FEM. FEM is a method for solving differential equations, right? But here I have no differential equation, not minimizing Galerkin's error, residual, or not using any functional minimization or anything of that kind. So, here, but it is, you can say it is like a numerical scheme. So, you can divide this window into each small component, and how much is the illumination coming through that dx dy element. So, and then contribution of each element you can find out and sum it up. So, obviously, you have to relate this to from the point that you are considering, right, viewing point, from the viewing point. So, numerical integration can easily be done, instead of for different odd limits of integration, you can do that actually today. So, that is not true, but then, and some of this sky model can be fairly, it can even become more complicated to get a kind of a closed form integration. It may be because A, B, C, D, E, etc. will go into, remember we talked about the ratio of brightness at a given point divided by zenith brightness is equals to some function of A, B, C, D, E, etc. zenith angle, and this angle itself, position of the sun and all that. So, it can become long expressions, integrating through closed form solutions may be difficult, but numerical integration is possible. So, I think that is all I wanted to tell it about the sky. I think all about the sky, others we have looked into. If you are interested, you can do a numerical modeling on